All right, so this is a video lesson for Unit 13, Lesson 2, which is graphing with transformations and the zeros of a quadratic. So this is two lessons put together into one lesson. We've kind of focused on the highlights of each of those lessons and put it together into one. So the first thing we're going to focus on is transformation form. So this equation right here, y equals ax squared plus c, is transformation form. Later in your math career, you'll learn about one more constant that can be thrown in here and how that affects the graph, but we're going to start off with a very basic form of y equals ax squared plus c, so we can focus on two of the very common transformations that you can see. So just to define what a transformation is when we take what's called a parent graph, which is the most basic graph possible for whatever family you're in. We're dealing with quadratics, and the most basic quadratic possible is just y equals x squared. So a transformation is when you start with y equals x squared, this graph, and then you change it, transform it into a new graph. So maybe that new graph is going to be narrower. Maybe that new graph is going to be wider. Maybe that new graph is going to shift down, but be the same. That's what we're going to learn about, is how we can take that first graph and then move it around or stretch it and change its shape. So that's what a transformation is. We have a couple of constants to pay attention to. First is A. A is going to scale the graph. We're going to learn about that in this lesson. And C shifts the graph up and down. We're going to deep dive on that to really see it, but that's what C does. Okay, so let's deep dive into C and start to see what this looks like, the effect that it has on the graph. So I'm going to start by graphing the parent function, y equals x squared. I'm going to start with that. And I'm going to use Desmos in this lesson. You don't need to, but I wanted to provide a visual as I do these problems. Okay, so what I've already typed in here is the x squared function. If you see in that box right there, it's x squared. That's what my y equals. So instead of having it as an xy table, it's an x squared table. And it's just going to produce the graph of y equals x squared for us. So we're going to use that as a little cheat to quickly get our graph. So we're going to put in those x and y ordered pairs. So -2, 4. I'm going to graph that on my grid. And I do want you doing this. You don't need to pull up Desmos, but I want you starting to jot down this graph. Okay, -1, 1, 0, 0, 1, 1, and 2, 4. So that is our parent function, y equals x squared. Next, I'm going to go and graph y equals x squared, and then plus 2. That's our next function, plus 2. Hit enter, and I'm going to shift this one again into being a table so you can see. Okay, and if you look at this graph, the first graph was in black, that was the parent, and now you see this green graph here, and you notice it's a couple of units higher. It's the same U shape, and let's make ours. Okay, so let's do ours green just like theirs. Doesn't have to be, but let's do green. Okay, and then I'll go to green. And we have -2, 6, so 2 units higher than the last point. -1, 3, which is 2 units higher than the last point. 0, 2, which is 2 units higher. And you see as I put these points on the graph, they're all 2 above the blue points. That's because C equaling 2, that constant being 2, shifts the graph up 2. So that's what C does. Okay, now let's confirm that for ourselves and maybe make a prediction, if you want right now, about what this next graph is going to look like. But we're going to do x squared minus 1. And I'm going to turn that into a table and take those ordered pairs. And if you look now on this graph, you see that the purple graph is a little bit lower than the black graph. Okay, and if we go and we'll do purple, if we graph ours in purple, we're going to see that we get -2, 3. So -2, 3, which is 1 unit lower than the blue point. -1, 0, which is 1 unit lower than the blue point. 0, -1, and you notice the trend. Every point is 1 unit lower than the blue points. And that's because we shifted the graph down 2 in this case. Sorry, down 1 in this case. So, summary. Let's get out of Desmos for a minute. When the C was negative, which was this problem right here, when C was negative, the graph shifted down. So it went down 1 unit compared to x squared, the blue graph. When C was positive, the graph shifted up 2 units, up 2 from the blue. That's what C does. So if I had an equation like y equals x squared plus 5, this 5 is positive, so it would tell me to shift up 5 units from what x squared looked like. This allows us to pay attention and know the details of one graph and be able to graph as many other graphs based on that one graph that we know. Okay, if you know x squared really well, you can graph x squared plus 2 or x squared minus 1 or x squared plus 5 with transformations. Now we're going to focus on A. Okay, we already know our x squared graph, so I'm going to pull back up our graphs. Okay, we already know our x squared. Our x squared was this first one. Okay, so I'm going to jot those down again. We'll do black since that's what this was doing here. So we'll go black with this. And we're going to get 0, 0, 1, 1, 2, 4, -1, 1, -2, 4. Okay, this is just our basic x squared graph. Our parent graph, it's called. Okay, and now we're going to pay attention to what happens when it's 1/2 x squared. So we're going to focus on the A now. Okay, when A is 1/2, what's this look like? So I'm going to do this on mine. I'm going to get rid of that plus 2, and I'm going to make this 0.5, which is 1/2. Okay, and what we notice here is the graph, if I get rid of this purple graph, you see that the green graph, the new one, is wider than the black graph, the parent function. Okay, so let's get those points thrown on here. Okay, we're going to go with green, and we're going to graph -2, 2. We're going to graph -1.5, 0, 0. That point stays the same. 1 and 0.5, and then 2 and 2. And we notice that the green graph is just a little bit wider than the black graph. So when we go here, we see that that U shape is a little bit wider. Okay? Now, let's take a look at the next one. I think we end up being purple for this one. Let's take a look at this 2x squared. So now I'm going to just change it on this one to 2x squared. Okay? And you notice that this one got narrower. Okay? Let's graph those points. We're going to do it in purple since I changed it on the Desmos. It's still green on Desmos, but let's go purple. Okay? -2, 8. 1, 2, 3, 4, 5, 6, 7, 8. -1, 2. 0, 0 again. 1, 2. And then 2, 8. And we see that that graph is narrower, skinnier, if you will, than the black graph was. So what A does is it makes the graph wider or it makes the graph narrower, which is also known as scaling the graph. Okay, and I want to kind of make a conclusion here about these first two before I move on. Okay, when A was between 0 and 1, and you can play around with this on Desmos to prove it to yourself, but I'm going to try to keep this a little bit quick. When a is between 0 and 1, it's going to make the graph get wider, as we saw there. Okay? It's compressing all of the y's. It's making them a little bit lower, which makes the graph turn out wider. Okay? If a is greater than 1, it takes all the y's and it makes them taller, which makes the graph skinnier. Okay? Or narrower. Then the last thing I want to focus on is what happens when we throw a negative in front of the x squared. So if we make a negative, what's happening there? So I'm going to go and just change this one to a negative x squared. And when that happens, what it does is it flips the graph directly upside down. Okay, so we're going to make this one red. And we're going to graph that. And we're going to see that it's going to make the graph directly upside down. It's going to be the same numbers, 1 and 1, 1 and 1, -2 and 4, but now it's -4, and 2 and 4, but now it's -4. So what this does, when x is negative, is it flips the graph upside down. Okay? A fancy way of saying this, the graph flips over the x-axis. So what you notice is it's the same shape as the black graph, our parent function. It's the same shape as this, but it's upside down. So we're still going to get that U shape, but sometimes it's going to point upside down. So let's move on from that now that we know what A and C do, and let's talk quickly about zeros. So the x-intercepts of a quadratic function. So if you don't remember, an x-intercept is where the graph hits the x-axis. So the x-intercepts of a quadratic function are also known as its zeros. And that's because the zeros, or the x-intercepts of this equation, whatever A, B, and C are also the solutions to this equation, whatever, if A, B, and C match. So if I have a question like y equals x squared plus 2x plus 5, if I graph that, the x-intercepts are the solutions to 0 equals x squared plus 2x plus 5, which is really powerful because if you think about it, we spent a whole unit trying to solve this problem. We did it with factoring, we did it with square roots, we did it with quadratic formula. Well, graphing is another way to solve these. If you can see where the graph hits the x-axis, you know the solutions. They're known as the x-intercepts or the zeros of the function. Okay? A function can have, and we'll draw it for you, it can have 2 zeros, it can have 1 0, or it could even have no zeros. See the number of times it hits? 2 times. This guy never hits the x-axis, and this guy hits 1 time. So now, let's put this all together. Explain the transformation that occurs when the graph of y equals x squared is changed to y equals x squared minus 5. Well, what I'm seeing in this problem is a -5 as the c. Remember, it's y equals ax squared plus c. I see -5 as the c. C shifts the graph up or down. Well, this guy is negative, so it's going to shift it down. So explain the transformation. The graph shifts because it's a c, down 5 units. That's all you got to say. That's how x squared transforms into x squared minus 5. Now, if x squared normally looks like this, then we can draw a rough sketch of x squared minus 5 by simply drawing it down 5 units. And we don't have to be perfect here. Just roughly draw it below the x-axis, which makes me realize it's at 5 units below, or it's below, which is really the only thing I care about. Okay? And then we just draw the same graph. So this is our rough graph. That's all they asked, a rough sketch. That's our rough sketch. We drew the same shape, but we made it 5 units lower, or we just made it below the x-axis. And if you draw this rough sketch, it doesn't have to be perfect. You can see how many x-intercepts there are, or zeros. This guy has 2 zeros because it hits the x-axis 2 times. Now, for this one, they ask us to describe this transformation. Well, what I notice here is that all I'm dealing with besides x squared is a 3 in front. That's an a. If we remember y equals ax squared plus c, a scaled the graph. If we go back up here, if a was greater than 1, it made the graph narrower. So our a here being 3 means the graph is going to get narrower, okay? The graph gets narrower, and we're just going to throw in the language by scale 3. We don't need to get too into this. Just use that language. The graph is going to get narrower, and we'll just say by scale 3. So what I'm going to do to draw this one is I am going to kind of dot a sketch of x squared. I could even write it off to the side if I really wanted to, okay? That's not part of my graph, but I'm just going to use it as a reference to show that I know that this graph is supposed to be narrower or skinnier. So I'm just going to draw a graph that is skinnier than x squared. So it helps to have it both on the same graph, just so that you can easily tell that this graph is supposed to be narrower than the original graph. It asks, how many zeros does this have? Well, I only see the vertex hitting the x-axis, so that means it has 1 0. So I'll go a different color. Right there, 1 0. One place where it hits the x-axis. On to example 3. In this case, we have a couple of transformations. The first one is that the graph is got a -1 in front, or a negative. So that means it's going to flip it upside down. Okay? The graph is flipped over x axis. I also have that it is shifted down 3 units. Okay, this one's a little bit harder to, and sorry, just to explain, that's because c was -3, so it's shifting down by 3 units. Okay, so this one's a little bit harder to graph. Okay, the first thing is I'm not going to draw my x squared here. I'm going to draw my -x squared. Okay, so that's how I'm going to start this off. I'm going to draw my -x squared because I know that it's just x squared flipped upside down. So I'm just going to draw an upside down x squared. Okay, so let me shift this up a little bit. I'm just going to draw an upside down x squared, and like I said, I'm going to do it with a dotted line so that nobody thinks it's part of the graph. Okay, so that's my x squared, but I'm graphing -x squared minus 3. I'm sorry, that's a -x squared. Okay, so -3 means I shift this down 3. So I'm going to draw the same graph shifted down a little bit to represent 3 units. Okay, and now I'm going to draw the exact same graph. Oops. And there we go. It looks a little bit narrower, but that's just because it's starting lower. It's the same idea, the same shape. Okay, and that's our graph of -x squared minus 3. How many zeros does this have? Well, it starts below the x-axis, and then it goes down. It's never going to hit the x-axis, so it has no zeros. If you start below and you go lower, you're never going to hit the x-axis. Okay, a couple more examples and then we're done here. Explain the transformation that occurs when y equals x squared is changed to y equals 1/2 x squared plus 2. So this has a lot going on in it. Okay, first of all, I want to deal with this 1/2. Okay, so that means the graph is going to be narrower, or sorry, wider, because it's between 0 and 1. The graph is wider by scale, you could say 1/2 or 0.2. or sorry, 1/2 or 0.5. And then it also and shifts up 2 units. And that describes the transformation. The original graph, y equals x squared, is wider by scale 0.5 and shifts up by 2 units. Okay? So what I can do here, if I want, is I can just draw a wide graph and shift it up 2. I do like to give that reference that this is, or that x squared looks like this in my, very rough graph. So there's my x squared, okay? And now I'm just going to draw a graph that starts above and is wide. So I'm going to start it at 2, and I'm going to make sure it's nice and wide. And that's it. It's a very rough graph. That's all I'm trying to do here is just make a rough graph. I'm showing that it's nice and wide, and it starts above where the y equals x squared graph started. Okay? With a little bit more room, I could probably draw this a little bit nicer. So maybe I'll do that just to make it a little bit prettier, because that one was pretty ugly. So nice and wide graph, wider than x squared, and starting above it. How many zeros does this have? Well, it starts above the x-axis, and it keeps going up. So it's never going to hit the x-axis. So I can say no zeros. Now, let's put this together one last time and just do some matching. Okay? So if I look at this, this matching problem, they've given us more options than problems. Okay? But we can actually match this up. So first of all, y equals negative x squared. This first one. It's not shifting at all, and it opens down. So I should see a graph that opens down, so not A, because that opens up, okay? Not D, because that opens up. It could be B. Not C, because, yeah, it opens down, but, so it's negative, it opens down, but it's shifted. It's supposed to start at the, look at y equals x squared in these graphs. Supposed to start, here, y equals x squared is the blue one. It's always supposed to start at 0, 0. So for this one, this graph right here in E, it doesn't start at 0, 0. It starts below. This graph here in C, it doesn't start at 0, 0. It starts above. This one here in F doesn't start at 0, 0. It starts below. So I can rule all those out, and B is the only one that doesn't shift and opens down. So we've got our first answer. Now this next one is supposed to open up because it's just x squared, and it's supposed to shift up too. So A opens up, but it starts at 0, 0, so it's not A. Now this opens down, so it's not C. F opens down, so it's not F. E opens up, but it starts below. Well, if it's 5, it's supposed to shift up, so it should start above the x-axis. So it's not E, and that means it's D. D goes up, and its starting point, the vertex, is above the x-axis. So that's D. Okay, next here, we have one that's negative, so it opens down, and it's negative for C, so it starts below. So we want something that opens down and starts below. And F is the only one I see that opens down and starts, its vertex is below the x-axis. So that's F. And then finally, last problem here, we want one that opens down and starts above. So can't be A opens up, can't be E opens up. How about C? Does that open down? Yes. Does it start above? Yep. That's the only one. And there you go. So you don't actually have to graph these. You just have to understand the features. If A is positive, we open up. If A is negative, we open down. If C is positive, we shift up. If C is negative, we shift down. If there is no C, there is no shifting. Okay? And the easiest way to figure that out, if it's shifted, is to look for the vertex. This guy's vertex is at 0, 0, so it did no shifting. 0, 0, it did no shifting. This guy's vertex is above, so it shifted up. This guy's vertex is above the x-axis, so it shifted up. This guy's vertex is below, so it shifted below or down. And this guy's vertex is below, so it shifted down. It's a good way to help you see how the shift is happening. Whether it opens up or down is pretty easy to see. But the shift, focus on the vertex. It should be on the x-axis, so if it's above, it's a positive c, and if it's below, it's a negative c. And that's it. That's the end of this lesson.